Hey Chemsters, this is Mrs. Vandoy bringing you Blankwalle, Chapter 14, Part 4. This is expressing the equilibrium constant in terms of pressures. Hey, let me show you something. Let's go back a couple pages. Here's problem 6. Do you notice I'm at problem number 6? They're all in terms of gases. Hey, let's look at the next page. They're all in terms of gases. Okay, so let's go to section 14.4. Here's an example. Hey, guess what? The products and reactants are all in terms of gases, okay? So because of this, I can have a equilibrium constant in terms of concentration. Folks, that's what we've been doing all in section 14.3. They were all in terms of concentrations. They were all using molarities, weren't they? But now we can also express these in terms of an equilibrium constant using pressures, okay? So what is the purpose of this section here? Well, we're going to see how are Kc and Kp related. Are they the same number? And the answer might surprise you because the answer is, well, sometimes they are, sometimes they're not. So where do we begin with this whole thing? How do I figure out how they're related? Well, we're going to start with piv inert. Piv inert is a great place to start for gases, all right? So piv inert. And now what I want to do is divide both sides by V. Why? Because now this term right here is a concentration, moles per liter. That's concentration. That's what we've been talking about. That's a molarity unit, isn't it? Okay, so they're going to represent that N over V by the capital letter C for concentration. So here we can say that the pressure of my system is equal to the concentration RT. But that doesn't really help if you have different concentrations. So let's use Dalton's law of partial pressure and break it down. So pressure of A is equal to the concentration of gas A times RT. Partial pressure B is equal to the concentration of gas B times RT, et cetera, et cetera. So now what? Well, let's use the law of mass action and come up with Kc. And notice I have the brackets meaning molarities in here. But what can I do? I can substitute my product C is equal to Pc over RT. My product D is pressure D over RT, and do the same thing for my reactants. So that's what this is going on right here. And don't forget, now you have the concentration. You still have to raise it to that power. Remember what I said in section 14.3? Those coefficients are going to be in terms of superscripts, of terms of powers, aren't they? So here is my law of mass action, substituting for concentration. And this next step is trying to simplify it. They're going to pull out a common term, 1 over RT. You can't cancel them out because your superscripts are not the same. The powers are not the same, or they don't have to be the same. Let's put it that way. So they're going to further simplify it and use this term, 1 over RT. And do you remember what your rules for dividing are? For if you have a power, you're going to subtract your powers, all right? So take your numerator power minus your denominator power, which turns out to be your product powers minus your reactant powers. Or you can say your product coefficients minus your reactant coefficients, okay? And so that's what this whole thing right here will turn out to be. So Kc is equal to Kp times 1 over RT, and then you subtract your coefficients, okay? And so rearranging it, well, why do we rearrange it? Because this is a little bit cumbersome, having this fraction here. So what if I multiply both sides by RT with its power there? Then the RT ends up on the Kc side, and there's Kp. All right, now just real quick, I just want to show you something. Take a look at this term right here. This is your Kp. This is using the law of mass action, just using pressures, all right? So if you just want to solve for what is Kp, all right, you can, instead of using concentrations, you can use pressures right there. Your pressures do need to be in terms of ATM, by the way, all right? But this right here, using law of mass action, is Kp. Okay, a little side note. All right, so back to this again. Here's my equation now, and now I have substituted right here C plus D minus A plus B for delta N. Well, what's that delta N? Delta N is your coefficients of your products minus your coefficients of your reactants, okay? In other words, it says the difference. You're subtracting, right? The sums of the coefficients for your gaseous products and your reactants, okay? So let me try to simplify this a little bit and kind of show you how I think of this. Maybe it'll be helpful. This is what I do. I start with Pivner. What a great place to start, all right? I'm going to divide both sides by V because this is my concentration, okay? So then I'm going to substitute pressure for Kp. You remember that when we talk about Ks, you always use those coefficients as powers, right? So any of those coefficients are going to be expressed with the Kp. Here's your concentration. So again, I'm going to substitute this N over V for Kc. Again, the Kc also will include all those powers of your coefficients. So if I'm going to substitute RT, I have to substitute for something that has what? Right here is your coefficients. Now, let's go back and look at our original questions. These. How are these two, Kp and Kc, related? I just showed you. They're right here. This is how they are related. That's the equation that relates both the constant for pressure and the equilibrium constant for concentration. All right, now what? Gonna go back up here. Are they the same number? And the answer might surprise you. The answer is sometimes. Well, let's answer that right now. When is that sometimes? Well, when is Kp equal to Kc? When this entire term here is equal, that's a nice equal sign, to 1. And when does that entire term right here equal to 1? When delta n is equal to 0, right? Because any number raised to the 0 power is equal to 1. So if your change in your coefficients, if your coefficients of your products minus your coefficient of your reactants equals 0, then Kp equals Kc. So let's see what this next page does for us, and maybe we'll see an example of that, okay? Let's go on to the next page. All right, so using the value of Kp equals 1.9 times 10 to the third, which is 1,900, by the way, calculate the value of Kc at 25 for this reaction, and here's the reaction, all right? So again, I hate to memorize. Let's see what I got. PV equals nRT. I'm going to divide both sides by V. So then if I want to go from P to Kp, I go from C to Kc. And now how do I go from RT? I go to RT raising it to some power. All right. So let's see here. Here's my equation. And now I'm going to plug in some numbers. All right. So Kp, they told me, is 1,900 is equal to Kc. That's what I'm looking for. Here's my R. Does that R look familiar? Going to go back and use the 0.0821. There's no energy associated with this, so you're not going to use the 8.314. Okay, go back and use your liter atmosphere one. Okay, and then here it has to be in Kelvin. Okay, and I'm going to raise that RT when I multiply the two together to the products minus reactants. All right, so here's my products, 2 minus, well, how many, what's my coefficients here? 2 plus 1 is 3, so 2 minus 3. Well, what's that equal to? All right, well, here we go. 2 minus 3 is -1, okay? You have your calculators. Hey, what's 0.0821 times 298? Go ahead and do that. Okay, what'd you get? This is what I got. I got 24.5 to the -1st. So what is 1 divided by 24.5? I got 0.041. How about you? So now what? How do I figure out Kc? Divide both sides by 0.041, and I got, what'd you get? 46,000. Okay, so that is your Kc here. Are they the same? No. Why not? Because your sum of your coefficients here is not equal to the sum of the coefficients on this side. Okay, let's look at number 10. All right, so consider the gaseous reaction. The carbon monoxide plus chlorine yields something. All right, what's the expression? All right, so go ahead, pause this, and come up with your answer and see how you do. Okay, hopefully you got it paused and figured it out. So I did this, Kp equals Kc, 1 minus 2. How did I get that? 1 minus, well, what's 1 plus 1? 2. And that's equal to, again, to the negative first. Is it always going to be negative first? The problem up here was, no, it is not. All right. So what does it mean when RT is to the negative 1? Where is it? It's in the denominator. So which one is that? Letter B. Is that what you got? That's what I got. Looks like problem number 11. All right, so here's the equation. Looks like we've got some hydrogen gas with iodine gas makes 2 hydrogen iodide gas. I have a Kc, and now you need to find Kp. Why don't you pause this and figure it out yourself? Come back when you're done. Well, welcome back. Hopefully, did you notice it was easier than what it initially looked at? Why is that? Because look at this. I have 2 minus 2. And so here we have Kp equals Kc times RT to the 0. What's RT to the 0? 1. So that's when we say Kp is equal to Kc, which is equal to 620. That's what this number is right here. Hey, that was an easy problem, wasn't it? So units of K, units of pressure must be ATM. Units of concentration must be molarity, but don't include any of those before. I told you that in section 14.3, didn't I? All right, so that concludes section 14.4. So don't wait to be great. See you next time. Bye-bye.